Very good morning, all. I think in this presentation we are discussing topic called fitness for service, level 3, and then remaining life assessment of critical piping and equipments of thermal power plant. So this image is the typical layout of a coal-based thermal power plant. So it's having different systems. Start from coal handling, ash handling, boiler, and then turbine, generator, cooling system, etc., and then all other supporting systems. So these systems, some of these systems are subjected to mechanical loading. Some of these systems are subjected to both mechanical and thermal loading. I'm referring the loadings because when systems are in operations, it's very complications to find out the remaining life assessment of that particular system when it is subjected to both thermal and mechanical loading, as compared to the systems which are subjected to only mechanical loading. In general, most of the coal-based thermal power plants are in operations more than their design life. Most of the power plants. This is because one concept, that is return on investment. So they invested huge capital on that plant, and then that systems need to be in operations for a certain period of life, extended period of life. So in this context, we have done extensive work on remaining life assessment and then fitness of service of some critical piping systems, and then we have suggested some design modifications and then design improvements using from the guidelines from different codes and standards. And then it's not only for standards, it's data collected, actual data collected from sites, and then NDT techniques, and then outcome from NDT. So with this, having said these are the major systems in coal-based thermal power plants. So here in this talk, I'm going to touch about only two critical systems. One is piping systems, which is connected from boiler to turbine, and then turbine components. It's both LP, IP turbine components, rotors, and then casings, both inner and outer casings. Okay, how do we do that one? How do we assess that? Why? Because that assessment word is very complicated. So how do we go for assessment? Then we, with extensive work on that, this area of assessment, and then work remaining life assessment, we have able to generate the flow chart, workflow chart, where we should start, and then using of different standard and codes. Why? Because once we have the systems, and then if the system is safe for next couple of years of service life, then we have a basis for that one. So for that one, we referred so many standards and codes from available like ASME and then API, and then some codes are from RCCMR. Why? Because creep related property is very difficult to get from ASME. And then I'm not going for in detail of each and every steps, but I'll take you through a simple example for each steps which we have done. So for RLA of particular piping system, it starts from the site visits. So these are the some simple example images which we have taken from the sites. And when we do this RLA of piping system for particular piping systems, each piping system will be having more than 180 to 200 kind of different type of supports. And then each supports, we visually inspect each supports and then take the reading of each supports both in hot and cold conditions. Why? Because that we need to check whether that support or hanger is in working conditions or in broken out or top out conditions. And then some supports are in damaged conditions. All these conditions are reported in a systematic manner and then submitted to authority for the further actions. So further actions means that they have some damage factor need to be rectified immediately during the shutdown, that they will go to take a call. Some replacement of hangers, they will take a time, and then they will decide, and then they'll go for a this is one first step of our assessment. So next is like, as I said, it is going for a remaining life assessment is going for a taking input from different aspects from site, actual data from site, and then NDT. So NDT is basically two major input parameters. One is thickness, and then some defects if it is found any defects. Thickness, if you can see that from the image, there is one line that is MS system, and then they will conduct thickness measurement on each pipe spool and then bench, and then our job is to consider each thickness, spool wise thickness, and then thickness in our analysis, to make sure that whatever we are assessing the remaining life assessment of the particular system is safe for next specified years of operations. So once we collected the information from sites, then we do the first stage is in the assessment is we do the pipe stress analysis, and then this is one of the example, just I summarized that one. So you can see this one. Then that particular system is not, it was not qualifying for occasional load cases because they are not considered during their initial stage in the design. So then we recommended some additional supports and then hangers, some stubbers, then to make sure this system is qualifying as per the standard codes like ASME B31.1. So not only suggesting, but we visit site and then we check the feasibility of the supports, whether that support can be added in the existing structures that and steel structures, and then we have suggested, and then like one not only for suggesting, then they will conclude. So where are the locations need to be taken care, and the support locations, and then we'll provide the type of supports to be replaced and then type of hangers to be replaced in a neat summarized manner. So this will help operators to take a decision and then go for a maintenance or like a replacement of a particular damaged hangers or supports. So like once we conclude the pipe stress analysis, so there are some challenges here. So here we cannot take the parameters like operations and then number of shutdowns. All these parameters we cannot take in the pipe stress analysis. Then we find out the solutions like then all these parameters. Why? Because once the temperature is coming into picture, creep will be in the phenomena in this particularly systems which are subjected to high temperature. Then all the temperature dependent mechanical properties, and then number of operation hours, and then number of shutdowns. All together, it will be a creep fatigue interactions that will be included in our analysis, and then consider the output from the pipe stress analysis, both stiffness of supports, hangers, everything are considered, and then we analyze the systems and then able to find out where are the critical locations, and then those locations, what is the remaining life of that one. Remaining life is calculated and then is suggested for these locations. Some of the locations are not fit for particular years of operations. Then we have suggested for some modifications like changing of particular pipe spool after so many years of durations, and then supports, additional supports like that. So this is up to, so one of the, this is one of the example where we compared. Why? Because remaining life assessment can be done using empirical formula as well, but that is limited for a ideal conditions. Like if it is a system and then we have a formulas, and then we generate the stresses and then calculate the values of what is the remaining life of that particular component, take parameters like LMP. So here including LMP parameters and analytical methods, and then both numerical techniques, we arrived the remaining life assessment of a particular system, and then it was a correlated, then it was almost matching with the whatever they calculated using empirical formulas. So like once we have the defects in the piping system, then we'll go for a detailed analysis using 3D CAD model, and then it should be qualified as per the API 579 norms, and then that is called limiting strain values. And then if it is limiting strain is not within the allowable limit, then we'll go for a suggestion like whether that component to be replaced or repaired, or it can be go for a further operations for particular year of time. So next is the with the conclusions, we will provide the where are the locations need to be monitored, and then where are the locations need to be replaced. All this information will be concluded. So one more challenge is like when we visit sites, most of the time we'll not having a complete input details which we need for our remaining life assessment activity. Then one of the technique that is 3D laser scanning. Then we have done the complete turbine assembly using the laser scanning technique, and then converted that laser scanning cloud basis to points to convert into 3D CAD model, and then thus 3D CAD model. This is the output from the 3D scanning of an entire turbine assembly. Then this turbine assembly is used for further RLA, FEA, and then RLA assessment. So then finally concluded that this particular component is having some high stress regions, and those regions need to be taken care during next shutdowns or need to be checked those locations. With this, I'm going to conclude my summary. So most of the coal-based thermopower plants are in operations more than their service life, but that need to be in service because of that intended was they invested a return on investment need to be taken care of that one, and then for that one we have worked extensively on the remaining life assessment of particular critical piping systems which are subjected to both the temperature and temperature, and then we have suggested some modifications to improve the system, and then those systems should be in operation for next specified years of life. Thanks.
Thank you, Shrikant. Now we can have some 4 or 5 questions, and during that time, speakers can come to the front.